Hi, welcome to Mine's a Pint Einstein, the science show. My name is Marcus Chown. I'm a science writer. I'm the author of books like Quantum Theory Cannot Hurt You, The Ascent of Gravity, and my latest breakthrough. And it's my great pleasure today to have with me Feryal Özel, who is a Turkish-American astrophysicist. And she's one of the key people responsible for creating the first ever image of a black hole. And that was of the 6.5 billion solar mass black hole at the heart of the nearby galaxy M87. So without further ado, welcome to the show, Feryal.
To be with you.
Now, well, thanks very much for your time. Now, you've just become the head of the Division of Physics at Georgia Tech, so congratulations on that. How's it going?
Yeah. It's going well. It's quite a transition, of course, when you take on a new role, but I've done quite a few of these transitions in my life. So I think I'm taking it in stride, and the people here are lovely. There's so much energy, so can't ask for anything more.
Now, you grew up in Istanbul in Turkey, so tell us about your journey. How did you get interested in astronomy, and how did you make the step from Turkey to America?
How much time do you have, Marcus? I mean, it's been a long journey. It's a cosmic journey of its own, in parallel to the cosmic explorations that I've done. But joking aside, yeah, I did grow up in Istanbul, Turkey. I went through high school there. I went to a really good high school that actually gave me some direction. Although I have to say my interest in science and math started even earlier. I really remember being like in third grade when I said, I'm going to study atoms. So I loved math. My mind works like that. So one of those like early exposures to a science encyclopedia where I saw the first drawing of an atom, and I was like, that's what I want to know. What is the universe made up of? And and then through high school years, that interest grew. I took a small detour at some point. I think it was around 11th grade, maybe 10th grade. I was like, maybe I want to do biology. But that was the only little detour. And then I said, no, I want to do physics. So then I came to the US to go to college at 17. New York City, Columbia, with 2 suitcases, transatlantic flight by myself, and found myself on a beautiful campus where I studied physics and applied math. And then it just went on from there. 1 year stint in Copenhagen at the Niels Bohr Institute, and then back to the US at Harvard for my PhD in astrophysics. So it's been quite a journey. I think this is the 4th distinct geographical location in the US that I live in after 19 years in Tucson, Arizona, moving to the south and back to the East Coast. It's been nice.
An interesting journey. I too arrived in America with 2 suitcases as well when I went to Caltech, but unlike you, I didn't continue and came back to England. Anyway, your interest, you seem to have an interest in extreme objects, the endpoints of stellar evolution, neutron stars and black holes. Is that your particular interest?
It is, and I'll tell you why. It's a secret. I actually love physics. I'm not one of those kids who grew up looking up at the sky and wondering about the sky itself. It's also really difficult in Istanbul to look, I mean, with the light pollution, big city, whatever, to look up and wonder what is the sky made up of. So my interest was always in like, what's the fabric? What holds the universe together? What are the subatomic particles? So my interest was always on the small scale rather than on the large scale. So when I started grad school, I was still interested in particle physics and theoretical physics. Then I realized I could do all of that, but actually have data if I did astrophysics. So the transition from the micro to the macro came very, very naturally, because in the 90s, it was already the golden age of astrophysics, new space telescopes, new ways of analyzing data, a bigger computing power was just becoming, coming into play. So I thought, that's what I can do. I can look for the extreme objects in the universe where matter is the densest, or magnetic fields are the strongest, or gravity creates the point of no return, and really try to use those settings to answer very basic questions about how does our universe work. So that's
interestingly, both of the extreme objects you talk about were discovered by women. Jocelyn Bell, who we interviewed last time, she discovered neutron stars, pulsars, and black holes were co-discovered by Louise Webster and Paul Murdin. Everyone's forgotten Louise Webster, but that's a really weird thing. So what is a black hole?
What is a black hole? A black hole is a extreme warping of space-time. I mean, really, the definition of the black hole comes from the solution to Einstein's theory that says, in this theory, you can form a singularity, which means an infinite energy density, and then it forms a volume around it where information and everything, matter, light, anything can go in but can't come back out. So it's an extreme warping of space-time that traps things. But of course, that's just a mathematical construct. We could have had that and not have black holes exist in nature. So the way black holes actually exist in the universe is they are the endpoints of very massive stars that once they run out of fuel and they start collapsing onto themselves, nothing can stop that collapse. So they actually, in reality, form these very, what we call compact or infinitely dense objects, which then live the rest of their lives getting stuff in, but not letting stuff back out.
And there are two basic types of black hole that we know of, aren't there? The stellar ones you're talking about, where a star blows itself apart, but its core implodes. But then there are supermassive black holes. What are they?
Black holes seem to live on a continuum as far as how massive they can get. Yeah, indeed, the ones that I talked about, we call them stellar mass black holes. If a single star exploded and left behind this remnant, they tend to be of the order of 10 times the mass of our sun, all the way up to maybe 100 times the mass of our sun. Honestly, before LIGO started observing these black holes on a regular basis, we didn't know that 50 to 100 solar mass black holes were really a common thing, but
that was the Gravitational Wave Observatory.
That is the LIGO Virgo Gravitational Wave Observatory, which is sensitive to black holes that are what we call binary black holes, basically orbiting around each other, and we can hear them due to the gravitational waves they emit, and we can see them with our laser interferometers. So those seem to be remnants of a single star. Well, a single black hole can merge with another black hole, but more importantly, if it's in the right setting, like in the center of a galaxy, where there's a lot of other stars and gas, and it has the strong gravitational pull, then it can also eat. So it can start growing bigger and bigger and bigger. And once you start on that path, then anything else that comes your way, that comes too close, becomes a fuel source for you. So then it's basically the black holes at the centers of galaxies seem to have gone through this rapid growth process where they became the dominant object at the centers of galaxies. But there are probably millions of black holes in any given galaxy. I mean, our stellar models tell us that there should be. We don't know all of them. Not all of them are active. They don't have a companion that they're sucking gas from. But so this two types of black holes that you mentioned, supermassive versus stellar mass, even if their origins are common, they seem to bifurcate, and the supermassive black holes are the dominant monsters at the centers of galaxies.
But they seem to they go up to something like 30 billion times the mass of the sun. I mean, really gigantic things.
Incredible. It's incredible, yeah. And every passing year, basically, there's a new record as far as what is the most massive black hole that we know. There's some uncertainty in the masses, especially of those more distant objects, where there are ways of estimating the mass, but it's not as nearly as precise as what we can do with our nearby supermassive black holes. But yeah, 30 billion, and they have formed within like 700, 800 million years of the beginning of the universe. Like that's pretty mind-boggling.
And that's a possible problem, because to get that big that quickly is hard to imagine, isn't it? I mean,
yeah, I mean, it's not that there isn't a path, it's just really difficult. I mean, how big were the baby black holes that formed at the beginning? And they like there is a natural limit to how quickly a black hole can eat, because the more mass comes in, the more light is generated, not from the black hole itself, but from the accretion flow, as it's falling in and heating up. It's the source of the light that we see in M87 and Sagittarius, our own black holes. But that light has a capacity to push back matter. And so it becomes a self-limiting cycle of, if there's too much coming in, then that gets halted. So that's what becomes challenging, honestly. Like how quickly can you grow and reach those types of masses within such a short amount of time?
You slightly preempted me, because I was going to say most people would think of a black hole as very small and black against the black of space, and so pretty much impossible to detect. But actually, we see many black holes are super bright. I mean, some of them are putting out 100 times the amount of energy of a typical galaxy of stars. Why is that? Is it because they're embedded in an environment, and that, how do they generate all? Again, I think people like Oppenheimer, who built was behind the atomic bomb. I mean, he wrote about the collapse of stars to form black holes in the 1930s. But he, like everyone else, thought they'd be black. And yet what we see when we look out at the universe is they're far from black.
That's true. So the object itself is black. No light is escaping from it. But because they have the strong gravitational pull, as matter makes its way into this gravitational well, it gains energy. It goes higher in temperature. And when matter gets to these high temperatures, and there's a magnetic field there, it emits light. So before it's really close to the black hole, before it's crossed that point of no return, actually black holes generate tons of light. They can. Some of them don't. Sagittarius A star, our gentle giant at the center of the Milky Way, M87, those types of black holes actually are pretty what we call quiescent and dim. But the types that you're talking about, generating factors more than the entire light from a galaxy during a rapid growth phase, that happens from the gas as it's coming into the black hole. Once it crosses, then you can't see it. That's why it leaves this telltale imprint on the surrounding light. So if a black hole was truly not interacting with anything in the universe, it didn't have a companion, there wasn't another star nearby that it could eat from, there wasn't a gas cloud or anything, then yes, they are dark, they are hard to detect. We try to see the distortion of background objects as if the black hole moves in front of them, but even that is a very, very hard thing to see. So
they're relatively small black holes. I mean, tiny things, but some of them are big enough and close enough that we have a chance of imaging them. Which ones are those?
Yeah, so you're absolutely right. Physical size of a black hole is tiny. So if you took our sun and squeezed it down to the size where it would turn into a black hole, this point of no return that we talk about, I don't even mean the singularity. The singularity literally is a point. We don't define a size for it. But let's talk about this horizon, event horizon, where this point of no return, it would be 3 kilometers for the sun. So physical size,
6 kilometers across.
6 kilometers across, the radius would be 3 kilometers.
Yeah.
So they're tiny objects, even though they contain this huge amount of mass. And that's what makes their gravity so strong, of course. A lot of mass in a very small volume makes them very dense and very powerful. So it's hard to find black holes that would be visible in the sky. And it wasn't until about the year 2000 when we started thinking about what are some optimal targets if we wanted to resolve, meaning like see the details like the image and that contrast between the no light and the light around. And we identified 2 black holes that were optimal for this purpose. One is the one at the center of our own galaxy, the Milky Way. We call it Sagittarius A star. It's towards the constellation Sagittarius, and it's the first radio source detected there. Sag A star for short. And that is basically our black hole. I mean, our massive black hole at the center of the galaxy.
Because every galaxy, as far as we know, has a supermassive black hole at its center for some reason.
As far as we know,
yeah.
The process of forming the galaxy also forms these supermassive black holes at the center. Ours is a lightweight, actually. It's just 4 million solar masses. But because it's relatively close, its size in the sky, I mean, we talked about this 3 kilometer radius, 6 kilometer across. When you take 4 million of that, it's bigger than the solar system, but still, as a physical size, it's fairly small. So,
are we having this conversation because we've got a very small supermassive black hole in the heart of our galaxy, thousands of times smaller than the bigger ones? Because in the galaxies with the big supermassive black holes, they tend to have these jets which stab outwards for millions of light years and disrupt the formation of stars and change the types of stars that form. Are we having this conversation because we have a small supermassive black hole in our galaxy?
I don't think I can definitively answer that. I don't think anybody else can either. It is true that some black holes have these more powerful jets, and when they are going through that accretion phase, that's that powerful infall of matter and the formation of these collimated outflows that we call jets, they tend to disrupt star formation in the centers of galaxies. Whether that would have affected the formation of a civilization on a planet that is, halfway out, like ours is a spiral galaxy, right? The Milky Way is a spiral. It's not an elliptical galaxy. And we're about halfway between the center and the edge of it. So we might have been okay anyway. I mean, yes, they put out a lot of light, and yes, they control the dynamics of the centers of galaxies. But probably, even if it's the galaxies going through these episodic high black hole activity periods,
we would be okay. Yeah.
I don't know. I mean, probably would. Yeah.
I think of these things as
all stars, that's what I'm trying to say.
Yeah, I think of these things as very tiny, and I suppose I think of them like a bacterium controlling the fate of Los Angeles or Istanbul. I mean, they are that small, and yet they have big, but their smallness is irrelevant, really. It's the amount of energy they pump out, and they control the galaxy. So it's incredible to think. Am I exaggerating by saying a bacterium that controls the fate of Atlanta?
Well, having seen what COVID did to all of us, I don't think that's an exaggeration. So
I'm thinking in terms of size rather than yeah.
Yeah. So I think Bacterium to the size of a city. I don't know that I can do the order of magnitude correctly in my head. Maybe it's a little bit, overshooting, but definitely they are small. And
I did that calculation, so that's
you
why.
did.
Yes, I
Oh,
did.
there you
So,
go.
so I mean,
Okay.
just because it just impresses me that something so tiny can have such an incredible effect on something so huge as a galaxy. But anyway, so to stand a chance of imaging a black hole, it's crucial to pick the right wavelength of light, isn't it? Why?
It is. Yeah. Yeah. So let me also say you had asked about the two sources that we had identified. And the second one is the supermassive black hole at the center of M87. And that's a much bigger black hole, but it's also farther away. So the size in the sky works out just right that it is just a little bit smaller than the angular size of Sagittarius A sky in the sky, or Sagittarius A star in the sky. So those two were the optimal, like if we were to get that resolution from telescopes to image anything, those are our best bets. But then what you said is absolutely correct. At what wavelength are we going to do this? And that's a somewhat harder question to answer because you have to understand the surroundings of black holes, their environments, and how light is being generated for that specific black hole in order to say a particular wavelength of light is able to get you to that point of no return, to the event horizon. So you want a wavelength that is basically that the black hole generates enough of, but not so much that it becomes opaque. It's like, otherwise it would just look like a torus surrounding the black hole. So I did that calculation in the year 2000 for the black holes that are in our vicinity, like Sag A star and M87, and found that 1 millimeter is the wavelength at which we can reach the event horizon.
And it's a sweet spot because you can reach the event horizon, but also
yes.
you can see sufficient detail to
Yes,
see it.
that's absolute. So there is enough light to see the contrast of the no light against it. So because if you go to certain wavelengths of light, there's just so little of it that you either wouldn't be able to see it or you wouldn't have the contrast, enough contrast with the black hole. So yeah, it is absolutely true. It's a sweet spot. Enough light, but not so much that it actually blocks your view to the horizon. And so that's when I, with a couple of colleagues, my advisor and a colleague at Harvard at the time, we started thinking about what are the sizes of black holes? What are
Was
the
that colleague your husband?
Yes, he is.
He might be.
He wasn't. We met working on this project.
Yes.
He was a fellow at Harvard, and I was a grad student. And we were working on these joint ideas together about what black holes look like, what does the accretion flow look like, and my advisor was one of the absolute brilliant leads in thinking about what type of accretion flow develops around them. So then I took it to the next level of, okay, if we wanted to see these things, what is the wavelength of light we would need to use? So that's how it developed.
And then to see sufficient detail, I mean, you need a large telescope because the larger the telescope, the finer the detail. But you can't have the telescope that you want, which is a telescope the size of the Earth. So you have to synthesize it. How does that work?
Right. So the technique, of course, predates our work in the year 2000. This is called interferometry, or aperture synthesis interferometry. Basically, the idea is that if I can't build a single dish, a single telescope that is big enough to get me the resolution, like my camera isn't big enough, my lens isn't big enough to get the resolution that I need, even for these optimal objects at the optimal wavelength. What I can do is take two telescopes, separate them by a distance, time tag them. So basically have them look at the object of interest at the same time, record the signals at the same time, and then after the fact combine these signals, basically matching up wavelength by wavelength. It's not exactly like that. Of course, the what we call the correlation process is a little different mathematically than what I'm describing here. But nevertheless, you match up these signals, and then you have the resolution as if your telescope dish was as big as the separation between those two separate telescopes.
So you use an array of these telescopes all over the world. But if I was to look at the Earth from the point of view of your black hole, I wouldn't see a filled-in dish the size of the Earth. I would see a kind of a moth-eaten dish, with just occasional telescopes. So
severely moth-eaten.
Severely moth-eaten.
Yes.
So obviously, although you get that, you can see the fine detail. It's not an optimal way of looking at this black hole. It's the best we can do.
Yeah, it is. It is the best we can do because you don't get the collecting area. Like you're not covering the entire Earth with the dish and collecting all the light that you can. You're not filling the entire Earth with individual arrays. We are limited by, of course, the land mass that we have. But it's not too bad, actually, because at this point, with the Event Horizon Telescope Array, we have one in the South Pole, we have one in the North Pole. We have one as far west as Hawaii. We have one in the Pyrenees. We're talking about new optimal locations. It's not enough to just like fill the Earth with small telescopes. They need to be sensitive enough. They need to be far away enough to get the critical pieces of information that you need. So you need some that are nearby, some that are really far away, so that you fill in all of that information by looking at it.
And if you were looking from the point of view of the black hole, their relative orientation would change as the Earth turns, so you get more information than you might expect. What I haven't introduced the Event Horizon Telescope, but this is the idea to have a dedicated kind of array of similar telescopes to specifically to try and image a black hole. When did it get started? I know you were one of the key people involved. When did it get started, and who was involved?
It was a very organic development for this project. I mean, as I was mentioning and we were discussing a little while ago, some of us started thinking about it in the year 2000. And the first official meeting where we said it's the inaugural Event Horizon Telescope meeting was in Tucson, Arizona, where I was. Two colleagues and I hosted that inaugural meeting in Tucson at the University of Arizona. And at that point, we still didn't have a collaboration agreement and a structure, but work was happening in parallel. The theoretical work was happening. We were going to funding agencies and getting parallel lines of support. The instrumentation work was happening, basically going to different telescopes and putting millimeter receivers on them, putting masers on them. So at that point, we were not a handful of people. I mean, the inaugural meeting was pretty well attended, but I would say a couple dozen people who were really interested in this.
Yeah, I mean, now many institutions and hundreds of scientists are involved in this project.
Yeah, we've grown a lot. I mean, it took between 2012 and 2017 our first full array observations. Of course, by then we did have a structure. We had analysis groups. We had project scientists. We had outfitted the telescopes. We had an analysis pipeline, all of that. But those 5 years were pretty intense. But 2017 to 2022 were probably even more intense.
So let's go back a little bit further. When was the moment that you knew it would work?
We had a lot of proof of principle observations in those intervening years, but only to test whether this millimeter interferometry would work between like pairs of stations or trio of stations. 2017 data is the first one where it was really like, okay, we have enough stations to potentially image the black hole if this whole idea works, if the surrounding of the black hole is how we modeled it. And by then, we had literally built new computer clusters that were faster than anything that had existed in science before. And modeled it in so many different ways to be prepared for possibilities of how to analyze it, et cetera. But it wasn't until the 2017 data was put together, all the data from the different telescopes that participated in that observation was correlated. We looked at the raw, not raw, but, you know, the not imaged, but interferometric data, like the...
So you can tell ahead of even making the image that you've got something.
Yes, because it was the telltale, when you have a ring or a disk in an image and you convert it into the interferometric data that we collect from the telescopes, it looks like a very particular function called the Bessel function. It has this ringing pattern, and our data was ringing. So we were we knew.
Now you observed in the spring with I don't know, 8 or 10 telescopes, you'll probably tell me, but why the spring? Was there a particular reason for observing in the spring?
Yeah, the visibility of sources, because we want to observe both Sagittarius A star and M87 and a few nearby quasars for which we don't have the angular resolution to go down to the horizon, but still they have jet structures, they have interesting things happening. So it's a combination of the visibility of sources, like how long they're going to stay above the horizon so that we can track them for a long night and get like with all pairs of telescopes, get a good look at from different angles, basically.
Yeah.
And weather patterns. The weather, when you're trying to coordinate a global campaign, weather tends to be a problem because, you know, you want good weather in 10 different places all at once. And I mean, 10 different places as in like Hawaii and South Pole and North Pole. So the historical observations had shown us that, or the historical data had shown us that the moisture in the atmosphere is lowest, and we have the best chances of clear skies for millimeter observations.
Because water vapor absorbs millimeter wave.
Vapor is the
high
nemesis.
and dry. Yes.
Yes.
So how did this work in practice? I mean, do you have a central control room like mission control, or is it nothing like that?
No, we did. We had a makeshift mission control room. We set it up in Cambridge, Mass. We literally carried desks and chairs and put up extra monitors and super high-tech whiteboard where actually it was me who was keeping track of all the info coming in from the various stations, so that exists in my handwriting. But that was just the first time around. By now, of course, we have VLBI monitors that are super fancy, user-friendly, automatically gets weather information and technical readiness information. So between 2017 and 2022, we learned a lot and changed things. But
it took you 2 years to reduce the data to produce the first image. Why did it take 2 years?
Variety of reasons, right? First, waiting for hard drives from the South Pole, because we set it up and then we ask for observations during the South Pole winter, and our colleagues there who are wintering over carry those out for us very kindly. But then there are no flights in and out of the South Pole, so you wait for the weather to get better. And the military planes to bring out the hard drive. So that lasted until November. And once we had the hard drives, then the correlation happened in 2 different stations, basically split in frequencies so that part of it could be done in the US and part of it in Germany. That got done. Then, as I mentioned to you, we saw that ringing pattern, but from that to saying that this is the unique solution, that this image is really uniquely because you don't have all the bits and pieces of information, you know, it's the combination of telescopes are giving you a lot of different features of this image, but to really fill in every pixel, so to speak, and to make sure that you're not generating something because of the assumption that you make or the methodology that you use, that uniquely you can determine what it should look like, takes a lot of testing, a lot of different algorithm development, a lot of theoretical additional tests that you run. What if? And M87.
I put up the image of it, by the way, so
Yeah,
people can actually see.
it.
I mean,
Yeah.
I actually think, I mean, I'm maybe very sad, but I think that's probably one of the most amazing images in the history of science. You know, I would rank it with the Earth rising above the moon, you know, photographed by the Apollo 8 astronauts, or, you know, the double spiral staircase of DNA, you know, because you are seeing, I think one of your physicists said, we're actually seeing to the end of space and time.
Yeah, it is. I mean, thank you for that. Of course, I feel that way about it. And
I'm not the only sad person. No, but it does show that this is the black hole in M87, and when we see the black region at the center, when this hot material goes over the event horizon, like water going over a waterfall, it's never seen again in our universe.
That's true. It becomes its own little isolated mini universe that we are not going to get any information from.
So we are, you know, a jumped up ape. You know, we evolved on an African plain 3 million years ago. We've done a lot of bad things to our planet, you know, but we've seen to the edge of space and time. That's something to be proud of. Anyway, so this was presented in April, I think the 10th of April, 2019, at multiple press conferences around the world. And you were in Washington, DC. Can you tell me about that day? You know, it must have been a really exhilarating day, you know, from when you got up in the morning, or maybe you couldn't sleep. I don't know.
It was an exhilarating day. I think I slept, maybe.
Did?
Yeah, but at that point, like, we just couldn't wait any longer to share this image with the world. Initially we were thinking we would do Sagittarius A star first, but M87 ended up cooperating more in terms of, you know, it's just bigger, things change less during nights of observations, and you're not looking through the disk of your galaxy, you're looking straight up basically to the M87 galaxy. And so those combination of factors, we decided probably in 2018 that we would publish M87 first. And I was leading the modeling and analysis, and what we can learn about Einstein's theory of general relativity from this image, which is very appropriate for our show today, of course.
Are we seeing the event horizon, so that the kind of black region inside the donut of hot material, is the edge of that the event horizon, or is it distorted in some way by the light being bent by the gravity? Are we seeing an image of the event horizon or the event horizon?
We are seeing an image of the event. What we're really seeing is the last point in which light can still go around the black hole but escape to infinity. So if you're a distant observer, there is a very big difference between a ray of light, a photon, that comes from a location, a distance from the black hole, where it can graze it, maybe even make a full circle or multiple circles around it, but come back out and reach you on Earth at your telescope. And the one that is infinitesimally closer to the black hole, interior to it, that just has no chance. It can't come out. It is bound to fall into the black hole. So there is this very sharp separatrix between light that can escape and light that can't escape. And because of the distortion of light due to gravity, that we call that gravitational lensing, that gets lensed to a particular size that is basically set by the black hole space-time. So we knew the size that we would see. So that's what you're seeing, the gravitationally lensed image of the separatrix between light that can come out and light that falls in, which is not the horizon, interestingly. It is called the photon.
The shadow? Oh, the photon orbit. Okay.
The photon orbit marks the edge of the shadow. That's that blackness that we see.
Is there anything else that you can tell us about this image?
Yeah. One other interesting thing that I find here is the slight difference in the brightness in the lower half and in the upper half. And that's because the gas around the black hole is rotating. And as it's rotating around the black hole, part of it appears like it's moving towards us, part of it appears like it's moving away from us. So that rotation of the entire flow makes the lower, in this particular case, I'm trying to trace it out with, like, if this is the spin of the black hole, the upper part is going away, the lower part is coming towards us, and that makes that asymmetry in this brightness.
Now, you also in that April 2017 observing campaign, you did observe Sagittarius A star, which is our own supermassive black hole, but it took you 2 more years to analyze that data. And I think you said it's because material was moving around thousands of times faster because it's obviously thousands of times smaller. So there was a lot of fluctuation. It was much more difficult to create that image. If that's correct, isn't it?
So the time scale with which things move definitely has to do with the mass of the black hole. So we were really bracing for the worst in that we were thinking that there might be a lot of fluctuation. We did not see as much fluctuation as we thought. There is a particular day where there's activity. Sagittarius A star has these events that we call flares that we've observed for many, many years at this point at different wavelengths. So there is that one really active day where there's a flare and we didn't image it. But the rest of the time, it is actually, of course, it's moving. There are subtle changes in the image and subtle changes in the way that we can reconstruct the image. But it wasn't nearly as violent as we thought. We thought it would really just like not cooperate and keep moving around and change the details all the time, which, of course, if you're observing for many, many, many hours trying to condense an image from all of those observations, it's not helpful if your subject is moving. But it did cooperate. It was just extra years of testing, extra years of trying to understand the effect of that movement, the effect of the looking through the disk of our galaxy, what we call interstellar scattering, and just trying to do our test of Einstein's theory even better than we were able to do with M87 because we knew its mass ahead of time. So combination of those things.
I mean, the striking thing is the similarity between these two images. And although that is how they appear to your telescopes, they have the same apparent size. In fact, M87 is about 1,000 times bigger. The ring is about 1,000 times, the black hole is 1,000 times bigger or more than Sagittarius A star. And yet they seem to be so similar.
Yeah, when I put these two images side by side for the 2022 press conference, because we wanted to really understand what is similar between them, what is different between them, what is it that we are excited about and learned new that we didn't know with the M87 image. So when I put these two together, they're pretty much true to size in terms of how they appear as an angular size in the sky. But like you said, M87 is about 1,500 times more massive. So its physical scale, if you were nearby, its physical scale would be 1,500 times bigger than that of Sag A star. But it is closer to 2,000 times further away. So you take a bigger object and you keep moving it back just a little bit further past the size that Sag A star appears. That's why I mentioned these are almost true to size. The Sag A star.
Because black holes, I mean, I think they are, there's an argument that they are the simplest bodies in the whole of physics. I mean, they're describable by just two numbers, aren't they? Their mass and how fast they spin. Almost like elementary particles. They're that simple. And this is this showing us that they are so simple that they're similar on all these different scales as well, because there are only two numbers to describe them.
Yeah, I mean, of course, part of our quest is to understand, is there another number that describes it, or series of numbers? So you said about the mass and spin being the two fundamental quantities, like an elementary particle, that describe these objects. If there was a third independent number that, for example, a quadrupole moment, that we could describe for or assign to black holes, then the image could have looked different. And depending on how you change the properties of the black hole from Einstein's theory, from the Kerr metric, from basically bread and butter description of what black holes look like, then both the shape and the size can change beyond what we can predict from just its mass. So the spin introduces a little bit of uncertainty, but it is small. It's just a few percent. So that's why just knowing its mass, you can say, is this consistent with the predictions of the theory for an object that we call the black hole? And could there have been additional quantities that describe the black hole, and how much can you push down on that space of possibilities?
Right. So what next for the Event Horizon Telescope? Are there other targets, other possible targets? Will you create movies? I mean, what is the next step?
So there are different directions to go from here. One that I'm very excited about is looking at these two targets at another wavelength of light. So we discussed at the beginning of our program how important it is to find that Goldilocks of wavelength. So there's a nearby wavelength. So this is at 1.3 millimeters, 0.86 millimeters. It's a bit shorter, so higher frequency, which allows you a little better resolution. But even more importantly, anything that has to do with how a gas emits light, like what we call plasma processes, that hot ionized exciting environment that's emitting light, when you change the wavelength of light, it will do something different. Whereas anything that's gravitational, so anything that has to do with the space-time of the black hole, does not care. So there are going to be constant features, and there are going to be features that change. So being able to now do this experiment in two different wavelengths of light and compare them, and compare the image sizes, compare the shapes, compare the various other things that we look at in the data, is going to, I think, just enable us to do even better tests of gravity, and just understand these objects more. Like, what does their environment look like? Do our theories really describe it well? We already know that our theories think the black hole should have been more variable than it is. So we already see small things that don't work, which we're very excited about. That's how you learn in science, right? You set up the experiment, see what works, what doesn't work. So that's one direction that I'm very excited about.
Now, Einstein's theory of gravity of 1915 has been tested and passed all tests, but only when gravity is relatively weak. So here we're seeing the example of where gravity is really strong. Is there a chance that we'll get some insight into whether the theory is, well, we believe the theory is correct, but I mean, it would be very exciting if there was if there was something that theory didn't predict.
It would be super exciting, because we think the theory isn't complete. It's not that we don't think it's correct in the sense that it's describing a bunch of things really well, but we don't think it's the full theory. It's not complete when it comes to merging the subatomic with how we understand gravity. And also, let me just add, you mentioned we've tested Einstein's gravity when it's relatively weak. So if by that we mean like gravity like in our solar system, or the two neutron stars, two pulsars at a particular separation, that's absolutely correct. But when it's even weaker, like in the cosmological setting, we have a cosmological constant that we don't understand the value of. So actually, is it entirely correct to say Einstein's theory passed all tests when at the galaxy and cluster scales we had to introduce, I mean, okay, naturally there is a constant there can be a constant in the equations, but why does it have the value that it has? That's ridiculously small. I don't know.
That's a very good point. Einstein's theory does not predict what we see in the universe at all, because we have to put all these fudge factors in. As you say, dark energy, dark matter.
Yeah.
It could be that there are subatomic particles which make up the dark matter that we don't know about. But it could be, as you say, that there's something wrong with Einstein's theory. I mean, it's amazing that it's been so successful that we ignore the glaring problem of that it doesn't predict what we see in the universe at large. But I suppose that's because we expected it to break down when it was very strong and not when it was very weak.
Absolutely true. I mean, it's a bit of a selective focus when we say it passed all.
Yes.
I mean, and to be fair, it does look like dark matter is more likely to be a subatomic particle. It's just that we don't know what it is. And when it's making up such a large percentage of the universe, and with our experiments at CERN and many direct dark matter detection experiments, we still don't have a clue really what it is.
If you're a betting person, surely you would think it was made of black holes, because we know they exist. But we don't know whether any of those hypothetical particles, which we've never seen in experiments or at a Large Hadron Collider, we don't know whether they exist, but we do know that black holes exist.
Yeah, we know black holes exist. We're not saying that dark matter is black holes, because there are many reasons why that wouldn't work.
There would have to be primordial black holes, wouldn't they? Ones that formed before the elements were made.
Yeah, I personally think that's not easy either, but they certainly can't be these black holes that formed from stars, because of, the counting doesn't work.
I mean, could it be that we think that the dark matter is made of particles because there are more particle physicists in the world than there are astronomers?
I don't think so. I think we're trying to look at the astronomical data as well as the particle data as objectively as possible. We don't know what it is. It's difficult to make it with a modification to our theory of gravity, but maybe we're not thinking right. So that remains to be seen. It would be wonderful if within the next decade we have at least some inkling what dark matter is.
Yeah. So, I mean, the basic problem with that we know of with Einstein's theory of gravity is it predicts singularities, so points of infinite density at the center, which of course are physically, mathematically nonsensical. So the theory predicts its own demise, really. So we know that there isn't a singularity. There's something in the center of a black hole, but it's not a singularity. But as you say, we would need a better theory we need to be able to unite quantum theory and Einstein's theory better to know what that is.
Yeah, absolutely true.
Yeah. Well, listen, thank you so much, Feryal. That's been really, really interesting. I hope that people have enjoyed their conversation. So thanks so much for your time.
I hope so too. And I was just thinking, it was definitely before the release of our first image that you and I did the first interview. So it's wonderful to circle back after 2 black holes and 5 more years and get a chance to chat with you.
Well, I'd like to talk to you again because I'm actually writing a book about black holes, so I'll be in touch.
In another 5 years, who knows what we will be talking about.
Absolutely. Oh, thank you so much. And really, thanks for joining us. And we'll do this again in a month's time. And my next guest will be John Mather, who is the man behind the James Webb Telescope. So until then, thanks for listening and bye.